All right, welcome to another exciting episode of AP Chemistry here at Spain Park High School. Today is Wednesday, February the 28th. Okay, one more day to Leap Day. Today we're going to be talking about LeChatelier's principle. LeChatelier's principle. Now look, LeChatelier's principle is an incredibly important life lesson because it's all about stress. And how do we handle stress? Okay? Well, LeChatelier's principle says that when a stress is applied to a system at equilibrium, the equilibrium is going to shift in such a way as to relieve the stress. So in other words, you have to do something to relieve the stress. Generally, whatever is causing you stress, you want to go the opposite direction, to do the opposite. And it's kind of ironic that it works out like this, because if you are stressed in your life, what you need to do is just do the opposite, which means it's desserts. It's the opposite of stress. And notice it has to be plural. You don't eat just one cookie. You have to have multiple. You got to buy the whole box, you know. So we want to do the opposite of that which is causing us stress. That's what LeChatelier's principle is all about. If you apply a stress, the equilibrium is going to shift in such a way, listen now, as to relieve the stress. So if I'm looking at a simple equilibrium, phenolphthalein is a weak acid. Now it's got a very, very complex, first off, it's a great spelling word because there's tons of wasted letters. But phenolphthalein is an indicator. It changes color according to pH because it is a weak acid. And we can let a weak acid just be HX. Any acid has hydrogen plus some anion X. Okay? The phenolphthalein X minus anion is pretty complicated. But if I have that in water, okay, then it's going to go in equilibrium and it's going to break apart into H plus and X minus. Here, when it's in the presence of a lot of acid, it's going to be in the molecular form and it's colorless. But when it's in the X minus form, it's that magenta color. Okay? So the way that an indicator works is that if I take an acid, I really should have brought a squirt bottle. If I take an acid and put some acid into this, and I put some phenolphthalein, just 1 drop or 2 drops in, it's colorless in the phenolphthalein. Now if I go and I start adding in some base, I don't know if I'm going to be able to get this into here. If I start adding in some base to this, swing and a miss. Okay, it'll turn magenta, but then it goes away. Why do you think it turns magenta on the top, but then goes away? Okay, because right now, base contains which anion? OH minus, right? So the OH minus reacts with H plus and makes water. So it pulls this out, okay, and makes more of it come this way. But it's only concentrated on the top. And so it's looking and looking and looking for more and more OH minuses. Ooh, I should not, that's probably going to contaminate that whole thing, but okay. So when I put that in there now, well, should I stay or should I go? Okay, so now what it did is we shifted the equilibrium to where now there's more X minus than there is HX. because I put enough OH minus in to where we reacted this plus OH minus, and that's going to H2O. But LeChatelier's principle is this. It's a balance. It's a teeter-totter. It's a seesaw. I see you, I saw you, I see you, I saw you. Okay? We're at equilibrium, we're balanced. But all of a sudden, the OH minus comes in and pulls H plus off the teeter-totter. It pulls it out of solution and changes it into water. So now there's a stress applied. We've thrown it out of equilibrium now. So now, again, what's the definition of equilibrium? Forward rate equals the reverse rate. Well, if all of a sudden I remove some of this reactant, what happens to my reverse rate? Does it speed up or slow down? It slows down, right? If I take some of the H plus out of the solution, the reaction is going to slow down. The forward rate isn't changing at all. So the forward rate is now faster than the reverse rate. So more of this comes over here to replace the H plus. The X minus builds up and it turns magenta to get back to balance. Now if I go back, if I go back and I add some more acid, the acid is only 1/10 as strong as the base, so we'll see if I have enough room here. Okay? At least at the top. Let's see if we have magic. Nope. Did I add the wrong one? Okay. Oh, there's the magic. Oh, magic. Okay. You think it's magic, but it's really just science. So what did I just do here? I'm adding more acid. So what did I do to my equilibrium? I shifted it back. Now I added a whole bunch more H plus. To where now when I have more H plus, what does that do to the reverse reaction? Speeds it up. So now it's going faster this way. So now I have more HX than I do this. So in essence, I'm like this. Here's balance. I'm at equilibrium. I add more H plus. Well, the H plus is right here. So I add more H plus. It's like more H plus jumps on my teeter-totter. So what does the reaction have to do to get back to equilibrium? It's got to go this way, make more HX to use up the H plus that I just put in. And so as a result, we get back to equilibrium, but now we have more of this. So I can push the equilibrium either way by depending upon what stress I apply. Okay? So the first principle about equilibrium, about LeChatelier's principle, and hey, does anybody speak French? Anybody take French? Okay. Seriously, I've heard this name pronounced so many different ways, and I don't speak French. If anybody knows French, what is the proper pronunciation of that?
I think Rick speaks French.
He speaks it, man. It's Italian.
Italian, never mind.
He's Italian.
LeChatelier. Yeah. LeChatelier. All right. I say LeChatelier because you don't really pronounce the last letters. But anyway, LeChatelier's principle. You apply the stress. So what we want to talk about today is what are the stresses and how do they affect the equilibrium? The first stress, okay? The first stress is adding or removing a reagent. That's what I just demonstrated. Okay? Adding or removing, listen ladies, adding or removing a reagent. On either side, really. And that's just your balance. That's like your teeter-totter. And use your pencil as a teeter-totter. If we add over here, now look, we're not talking about what the initial thing does. Adding more reactant makes it go down on this side. So what's the equilibrium have to do to get back to balance? It's got to shift right towards products. Okay? So it's when we ask the question, how does adding more reagent? Well, the first initial thing is it throws it out of whack. It makes more reactants. But it's going to make the forward rate increase. It's going to shift the reaction to the right. Now, does this change the value of K?
No.
No, what's the only thing that changes K?
Temperature.
Temperature. Okay? So it's going to shift it to the right. It's not going to change. K is still going to be. So we have to readjust this. So if I add in more reactants, well, that's going to mess up this ratio here where it's no longer going to equal K. So reactants, this is too big. So reactants has to decrease. This has to increase to get back to the ratio to where it still equals K. If I add more product, now all of a sudden this number is too big and it's no longer equal to K. And so this number has to decrease, this number has to increase until it gets back to what the original value of K was. But just think of the teeter-totter. How's it going to shift? Which way is it going to go? Okay? Another stress is increasing the pressure. Okay? Increasing the pressure. Now, I don't really like using that term like that. Okay? The reality is the way we increase the pressure is by changing the size of the container. Okay? If you change the size of the container, if you make it smaller, that's going to increase the pressure. Okay? That's the same thing as increasing the concentration of the gases. So all of a sudden everything's going to be crowded now, right? So the reaction is going to shift in such a way to make it less crowded. So it's going to go to the side with fewer moles of gas. So it's, if one side makes 2 moles of gas, the other side makes 1 mole of gas, well, it's going to go to the side that only makes 1 mole of gas because then they're not going to be as close together. You're going to change the concentration. The reverse is true. If I have a piston and I increase the volume, what's it going to do to my pressure? Decrease the pressure, right? And so if the pressure is decreased, now we got all this space we have to fill up. So it's going to go to the side with more moles of gas. Adding a catalyst, no effect. A catalyst is neither a reactant nor a product. It just gets you to equilibrium faster. So adding a catalyst has no effect. Now changing the temperature. If I have heat on this side, if heat's on this side, if I add heat, which way is it going to make it want to go? Right. If it heats over here on this side, exothermic, which way is it going to want to go?
Left.
Back left. It goes away from whatever you're adding. You're going in the opposite direction of whatever's causing you stress. Okay? So let's look at some here just in your notes. That's page 10 of your notes. Let's look at page 11. I want to put it over here so we can't. Maybe don't turn to page 11 because I don't want you to see the answers. Okay? Predict. Okay? Predict the equilibrium shift when the volume is reduced. Okay? The volume is reduced. So here we have this, we're at equilibrium, and then all of a sudden we're going to reduce the volume, make it smaller. Which way is this equilibrium going to want to shift?
Right.
Why to the right, Ocean?
Because there's no moles of gas on the right.
Okay, there's no moles of gas on the right, so it's going to go to the side with fewer moles of gas. The less space you have, now again, it's only gas, but the less space that you have, the fewer moles of gas you want in your reaction. The more space you have, the more moles of gas you want. Because gas is what's going to fill that space. Does that make sense? So try to think about this logically. These will be pretty easy if you just kind of think about it in a logical sense. The preparation of gas is here. So we have 2 moles of gas, 1 mole of gas. I decrease the volume. Which side is going to want to go to?
Right.
It's going to want to go to the shift. So we say the equilibrium will shift to the right to produce fewer moles of gas. And then here, ooh, this is complicated. 1 plus 3 is 4, 1 plus 3 is 4.
So you're just saying.
It's not going to go either way. It's not going to favor either side. Does that make sense? All right, let's look at some in the book. Well, actually, let's go ahead and do this last one here, and then we'll go to the book. Okay? This is temperatures increased. Now, a positive delta H. Which side of the equation does it go on?
Left.
Make sure we know this, okay? Because when I was just looking at your eyeballs on some of this, there wasn't a lot of confidence. Okay? We need to know a positive delta H means it's endothermic, which means heat's going to be on the left-hand side. A negative delta H means it's what? Exothermic. Heat's going to be on the right-hand side. That is got to be just instinctive. We have to know that. So whatever it takes for you to know that, because we've struggled with endothermic, solutions getting cold, exothermic, solutions getting hot. We've talked about it. We've got to know positive is going to go, the negative is going to go over on this side. So if I increase the temperature on this one, which way is the reaction going to go? It's going to go right. If I increase the temperature on this one, it's going to go left.
So this was asking how the value of K would change those.
Okay, now, okay, so that's shifting. So again, K is a relationship of what? Products over reactants. So if it's positive and I increase the temperature and I shift it this way,
Increasing the product.
more products, less reactants, so what happens to K? It gets bigger. And then here, I'm shifting it the other way, so now we have less products, more reactants. It becomes more reactant favored, K decreases. All right? That's really as hard as LeChatelier's principal problems get. The reality is I pray for a bunch of those type of questions because they just are they just go left and right. You just kind of go away from whatever you're adding. So let's look in the book. Let's go to the good book. Your chemistry book. Let's put glasses on so you can read it. Page 666. 666. The devil's page. 666. Just look at this. You just go over here. All right. Consider the following, and it says delta H is less than 0. Does that mean it's positive or negative?
Negative.
So where in the equation does it go?
Right.
On the right side. So you can just like plus heat right here in your mind. Okay? We got to know, be able to understand that. Okay? Whatever it takes, you've got to figure that out for yourself. Okay? I can say it, I can show you, but you have to figure out how to make that work in your brain. Okay? Because that's going to be asked over and over and over and over and over and again. So heat's over here. How will each of the following changes affect the equilibrium mixture? So oxygen is added to the system. So which way is the equilibrium going to shift?
Right.
To the right. You're adding this, it's at equilibrium. You add oxygen. To get back to balance, it's got to shift right. So, so this concentration is going to go down. Look, this concentration is going to go down. This concentration is going to go up. But I added SO2. So initially, this is going to go up. It's going to shift right, and it's going to come back down. But because this number is smaller now than it was before, this number is still going to end up being a little bit bigger than it was before because of the ratio of products over reactants. So if I added oxygen, the final equilibrium value is still going to be greater. So you're going to add in 10, but maybe 8 shifts right, so we have an additional 2. Okay? But this for sure, we're not adding any of this, so as it shifts right, this goes down, and that one goes up.
But is there more on the other side? So
Yes.
So the ratio.
The ratio's K stays the same. It's going to shift until you get the ratio of K, products over reactants, back to where it was before, because we did not change the temperature. All right? The reaction mixture is heated. So again, where's heat in the reaction?
Right.
On the right, so which way is it going to go?
Left.
Left. So this goes down, these both go up. The volume of the reaction vessel is doubled. So we go from here to here. Which side is going to favor?
going with more gas.
Bigger volume, you're doubling the volume, so you want to fill the space, so you want more moles of gas. So it's going to go from 2 to 3. So it's going to go left. Okay? A catalyst is added.
So it's machine.
Nothing.
It's not gonna change.
No effect. No effect. Gets the equilibrium faster, but no effect. By the way, another thing that has no effect that didn't get mentioned is adding a noble gas. If you add something that's not an inert reactant, that's why I don't like the increasing the pressure terminology. Because we could add in some nitrogen or neon gas to this, and the total pressure of the system is going to increase. But you didn't change the pressures of these at all. The partial pressures of these didn't change. So that's why I always want to go container size. So I don't like the questions that say you increase the pressure, because I could put in a ton of neon, the whole pressure of the system increased, but it's not going to affect the pressure of these gases at all. So it's not going to have any effect. The total pressure is increased by adding a noble gas. No effect. And then lastly, SO3 is removed from the system.
Right.
So it's got to go back to replace the SO3 that just got removed. Now, again, in terms of kinetics, I remove SO3, so what does that mean about the rate of the reverse reaction? It initially slows down, right? The forward reaction is still the same speed. So, in essence, okay, if I'm removing this, it's shifting to the right to replace it. It's going faster to the right until this builds up and this goes down, and they get back to that same rate. Okay? So in terms of kinetics, we understand in terms of as you change the concentration, you change the rate. So sometimes on an AP test, they'll ask in terms of LeChatelier's principle in kinetics why that happens. Well, as you remove this, the rate of the reverse reaction slows down. The rate of the forward reaction stays the same. And so initially, this builds up. Again, if we go here, this slows down, so it's going to shift back to replace it because the forward rate's faster than the reverse rate until they eventually balance out again. All right, see how it's all kind of coming together here? This is how chemistry all works. We're starting to put all the different pieces of the puzzle together. We're starting to understand more, and that's what makes chemistry so doggone interesting. Who had a hand up in the back? No? That was just a fake? All right, let's look at 62. Just see if you can just do 62. And I think it goes up onto the next page too. So let's do A, B, and C, and then we'll come back to it. Just do A, B, and C, just in your head, in your notes, however you want to do it. Making sure we understand this concept. Number 62. Today is Wednesday, correct? Will everybody be here on Friday?
No.
No.
Really? What are we missing for on Friday now?
I'm going for a college visit.
College visit? Is everybody gonna be here tomorrow?
I won't be here.
Huh?
I won't be here. I have
What's the field trip for this time?
for health science varsity.
I'm just saying, we've had more field trips and more law and DECA and, I mean, they're all great things, but I swear, I can't have a full class more than one day a week. Yeah. Do we have something during AO tomorrow?
On Friday.
Well, Friday is already, what, is it just 2 people going Friday? Let's see, yeah. It's Friday. We can't come to school on Friday. We're gonna. Let's plan on doing a lab tomorrow.
Wait, we have a lab?
We'll do a lab tomorrow.
Wait, I wore my only pair of pants today.
You either hopefully don't sweat in them or wash them tonight.
Are you
Hey, it's supposed to be even colder tomorrow than it is today. Tomorrow.
I'm wearing for 8 by 7.
It's supposed to be, hey, at some point this afternoon, the temperature's supposed to drop by like 30 degrees in 30 minutes. Yeah.
Well, I have to.
Yeah. Okay, now look. Okay, have we gotten A, B, and C?
Yes.
All right. So Amber, increasing NH3, what's that going to do to my NO? Because the question says, does this increase the yield of NO? So if I increase this, which way is it going to make my reaction go?
Right.
So what does that mean about this? Going up, down, or staying the same?
Up.
Up. Thank you, Amber. Okay.
What?
Wait, did she?
Yeah.
Did she say it?
Okay. What if I increase the H2O? A hill. If I increase the H2O, which way is the reaction going to shift? Left. Okay, the other right. Okay, left. So what's that mean about my NO concentration? It's going to go down. Now, what if H2O is a liquid?
You're right.
Would changing the H2O have any effect if H2O is in the liquid state?
No.
Why not?
Liquids and solids.
Aren't in the equilibrium expression, so it doesn't affect the value of K. So if you change the amount of solid or liquid with LeChatelier's principle, it's not going to have any effect.
Wait, why?
Because it's not in your equilibrium expression, because if you have solid, you add more solid, it's just going to sit on the bottom.
Oh, okay.
Okay? Solids and liquids, the concentrations are pretty much considered constant.
Wait,
So
so gases don't react with liquids? Like
Okay.
I said, Coke.
they do, but again, they don't affect the equilibrium position. Okay? They just don't. And as far as an explanation more than that, wait until you get into college and take an upper level chemistry class and they'll go into more detail. What if we decrease O2? If I decrease O2, which way is the reaction going to go? Left. So what's going to happen to NO, Raina?
Decrease.
It's going to decrease. All right? So let's now go to the, keep that reaction if we can in mind. Can we see these here?
Yeah.
Okay? So we decrease the volume of the container. We decrease the volume of the container. Okay? Which way is the reaction going to favor if I decrease the volume, Luke?
Left.
Why?
Because there's less moles of.
So we got 10 and we have 9, so less moles of gas, so it's going to want to go decrease volume, goes to fewer moles of gas. Now once again, if this were a liquid, you only count gas. So it'd be the force, so it would come to the right instead if this were a liquid. Okay? So if liquids and solids don't have an effect on the equilibrium constant, they don't have an effect with LeChatelier's principle. Only gases and aqueous. Only gases and aqueous. And then lastly, what's the last one that say? Okay, so we add a catalyst.
Nothing happened.
No effect, but increased temperature. Because this is negative, it's what? I think you're saying it goes to the left, right? Where does heat go in the equation?
Right.
On the right. That's what I was asking. That's why I was making sure that I heard you right. Okay, so the heat's going to go on the right. So increasing the temperature is going to push it left. So what would happen to the value of K?
More reactants. So
More reactants, so K is going to be less. It's going to go down. All right? So again, what's the only thing that's going to change? All of these other things, do they change the value of K?
No.
Only the change in temperature changes the value of K. All right? That's all there is for LeChatelier's principle. All right, and that's what our lab is actually tomorrow. We're going to do 4 different reactions. 4 different reactions, and we're going to shift it left, right. We're doing different stresses. Okay? And then we'll finish the lab by coming in here and eating desserts. No. That sounds like a good idea, but somebody's got to bring something. I just made that up. It just came into my head like that'd be a great finish to the lab. Oh, it's always on me. Okay. Okay, so here we go. Now, our last concept for chapter 15. Last concept for chapter 15 is the most challenging concept. And it's only challenging because it's stealthy. Not healthy, stealthy. Stealthy means it's hard to see. Okay? And it's called a Q problem. A Q problem. Reaction quotient. I know, but I'm just going to introduce it. We'll do the lab and we'll talk about it again on Friday. But I'm not going to waste 10 minutes. Okay. We're going to go back to the future with our notes. Okay? All right. Here we go. The reaction quotient. No, listen. Reaction quotient. Now they actually use Q for the reaction quotient. This is page 6. Page 6 of your notes. Page 6 of your notes. Not practice problems, but notes. Page 6. Okay? Now, Q is calculated the exact same way as K. The only difference is K is at equilibrium, Q is at any conditions. So Q is more like your initial, what we put in there, and we use Q to determine if the system is going to be at equilibrium, and if not, which way is it going to shift to get to equilibrium. Okay? Which way is it going to shift to get to equilibrium? All right? So if I look at this problem right here, you calculate Q exactly the same way as K. Solids and liquids are ignored. The products over reactants, coefficients raised to powers. There's nothing different between Q and K, except K is always just equilibrium concentrations. Q is any concentrations. And then we have to compare Q to K. Now the reason why I say Q problems are stealthy is because they generally don't say it's a Q problem. They generally ask a question, which way will the equilibrium go? Which way will the reaction go to reach equilibrium? Is the system at equilibrium? You know what? Sometimes we just have to know they give you everything. What are we looking for? So for the synthesis of ammonia, the Haber process, okay? Predict the direction that the reaction will go. Do they give they don't give the reaction. But they always assume that you know this one. And so, but the reaction will be given. So the Haber process, N2 plus H2 gas, and it's 3 of them, goes to 2 NH, N, Steve, NH3 gas. And again, this is known as the Haber process.
Do we have to memorize that Haber process?
No, again, the more you're just aware and familiar, so if they say it in an AP test, you're just going to be aware of that, okay? It's just making ammonia. So we make this, so here now we have all of this. So here, for the system of ammonia, the equilibrium constant, so they're giving me Kc. Right there. The equilibrium constant, Kc, is that. So I know Kc, and I know all of my equilibrium concentrations. So what do I find? All right? Well, in order to know if the system's at equilibrium, the question is generally going to be, is the system at equilibrium? If not, which direction will the system go? Anytime you have to determine the direction of the reaction, all the ones we've done so far, there's always been 0 on one of the sides. So we know it's going to go towards the 0. But now we have everything on both sides, so we don't know which way it's going to go. So you have to calculate Q, compare it to K, and find out which way it needs to go. Does Q need to get bigger or smaller to equal K? So we find Q. So Q is going to equal products NH3 squared over N2 times H2 cubed. So we just plug in NH3, 1 times 10 to the minus third squared divided by N2, 1 times 10 to the minus 5 times H2, 2.0 times 10 to the minus third cubed. Anybody want to do that one? So it's going to be 10 to the 6th. This is 10 to the minus 9, 10 to the minus 14, 10 to the minus 6. So it's going to be plus 8. So it's going to be 0.5 times 10 to the 8th. So it's going to be 5 times 10 to the 7th. Huh? Yeah, they're all gas. Did I get it right?
1.3, 1.25.
Oh, because I didn't
Yeah.
cube the 2.
2 cubed.
I didn't cube the cube, so it's 1.
The cube.
All right, so what do we get?
1.3 times 10 to the 7.
Times 10 to the 7. Okay? Really, it's 1.25 because it's 1 divided by 8. Now look, so here's Q. They give us K. K is 10 to the minus 2. Q is much, much larger than K, correct? If it's at equilibrium, they will equal the same. So this system is not at equilibrium. So the question is then, which way does the reaction have to shift to make Q equal K to get the system to equilibrium? So because it's a ratio of products over reactants, Q is way too big, which means I have way too much product, not enough reactants for it to be at equilibrium. In order to make Q equal K, I've got to have a lot less of this and a whole lot more of that. So the reaction has to shift left to reach equilibrium. Okay? It's a ratio of products over reactants. Right now, the ratio of my products and reactants is 10 to the 7. Well, once it's at equilibrium, the ratio has to be at 10 to the minus 2. So right now, the ratio of this products to reactants is way too much products. So it's not at equilibrium. It's not where it wants to be at equilibrium, if it had like emotions and desires. In terms of energy, in terms of equilibrium, in terms of all the reaction stuff, the chemistry stuff. So in order for the reaction to get to where the ratio equals this, we have to reduce the amount of NH3 and we have to increase the amount of reactants. So the reaction has to shift left. So if I just dump all of this stuff into a container, the reaction is going to go and we're going to produce a whole lot more nitrogen and hydrogen and a lot less ammonia until the ratio balances out to equal that number. All right? So if we do the exact same thing on this one, okay, you plug them all in and you compare them, I would bet that this time it's going to come out to something 10 to the minus 4, 10 to the minus 5, 10 to the minus something smaller.
It's a no shift.
It's a no shift? It's exactly the same? Oh. And then the third one, do they give you the answer down there as far as what Q equals?
Well, it just says shift, right?
Okay, so what does that mean about Q then?
Less.
It's going to come out to be less than K when you just plug these numbers in. So you calculate Q in the exact same way in which you calculate K. It's just you have to have K to be able to compare Q and K. If Q is larger than K, it's going to shift left towards reactants. If Q is less than K, it's going to shift towards products to reach equilibrium. Q is when the system is not at equilibrium. K is all the values when it is at equilibrium. Okay? So Q is going to be more of an initial state. When you just first put the stuff in, which way is it going to go to get to equilibrium?
So the way to know it's, if we're doing Q, it gives you like everything.
Yeah.
You don't know.
And the biggest thing is the question says, which direction will the reaction go? Is the system at equilibrium as a clue? No, the LeChatelier is the system's at equilibrium, and then all of a sudden you put a stress and throw it out of equilibrium. And then what does that have to do to get back? This one is more mathematical. You put everything in, and is it at equilibrium? Well, you got to figure it out by calculating Q, comparing it to a given K. All right, so if the question asks, if any way you have to determine which direction the equilibrium goes. Now, if we had that one problem, I think it's the one we did yesterday, 2000 and the very first one, 2003B. Okay, let's look at F. Remember I said we couldn't do F? You guys thought I was going to quit. I know, we have a few minutes. So if I look at this one here, okay, and it says at 1,000, the value for Kc is this. In an experiment, 0.75 moles of HI, 0.1 mole of H2, 0.5 moles are placed in a 1 liter container and allowed to reach equilibrium. Determine whether the equilibrium concentration of HI will be greater than, equal to, or less than. In other words, which way is the reaction going to go? Is HI going to get bigger? Is it going to get smaller? Is it going to stay the same? If it's at equilibrium, it'll stay the same. Now, nowhere in this problem is Q mentioned. But we're given K, and we're given all the concentrations. And it's asking, is HI going to get bigger, smaller, or stay the same? In other words, is the reaction going to shift right, left, or are we already there? So you go through and you calculate the value of Q and compare it to K. Yes, ma'am?
If we had to like show our work on the exam for a problem like this, if we just put Q, like we don't have to explain that, like they.
No, you just say Q equals.
Okay.
So we would say Q is equal to, now again, what is the reaction? Is it H2 plus I2 going to HI, or the other way? So the reaction is 2HI going to H2 plus I2. So Q is going to equal, the H is 0.1, the I is 0.5, and the HI is 0.75 squared. So can someone just do that super fast? We got 30 seconds. Come on. We got 45 seconds actually. Somebody do it for me. Come on. So it's 0.05. I don't know what 75 squared is though.
0.08.
Point what?
0.89.
0.89?
Yeah.
Okay? Where this is 0.026. Right? So is this bigger or smaller? Bigger. So Q is bigger than K. So which way is it going to shift?
Left.
It's going to shift left. So what's going to happen to my concentration of HI?
It's getting bigger.
It's going to go up. It's going to increase. So, and your answer would be, because Q is greater than K, the reaction will shift left, increasing the concentration of HI. That was a wonderful day. Lab tomorrow. Remember to wear your long pants, closed-toe shoes, and have a wonderful day.
Remember, if you like this video, like, comment, and subscribe.